Good morning, ma'am. See, good evening, ma'am.
Yes, good evening. Okay, we will start the session. Maybe we should wait for another 2 minutes and then we'll start.
No, ma'am, we can wait, ma'am.
Yep. I think we can start now. Let me present my screen. So, have you gone through the lectures?
Ma'am, only off only I referred, ma'am.
Uh, Sorry, have you started watching?
Only one lecture, ma'am. I
Only
think,
one.
yeah, ma'am.
Okay, okay, only one lecture. So, do you feel any doubt about that lecture or
Yeah, ma'am. More I'm having them.
you have doubt? You
Yes,
can
ma'am.
ask. Okay, you can ask your doubt then. You can ask your doubt.
Ma'am, can you tell about that pinch roller mechanism, ma'am?
Pinch roller mechanism. Okay,
Yeah,
one. And after, anything else?
fused deposition modeling.
Which fuse deposition?
Yeah, ma'am.
Okay, okay. So, any other doubt you have, or only two?
Having, ma'am.
Okay, Okay, so first is I will tell about the fuse deposition modeling. So in wire-based additive manufacturing, this fuse deposition modeling is one type of AM process by which you can print metal and polymer both. So let me just check whether the recording is on or not. I think it is on. Yes, it is on. Okay, so in FDM, you can print polymer and metal both. So the mechanism for polymer and metal is similar, only different is the temperature. So for polymer, obviously the temperature is much lower than the metal. So then question comes, temperature of what? So for that we have to understand how FDM works. So FDM is fused deposition modeling. So in fused deposition modeling, what happens is there will be a spool of wire. So this is a spool. In this spool, your wires are winded over the spool. Okay. So now from this spool, the wire is coming to the pinch roller. So there is one mechanism called pinch roller. So then through the pinch roller, it is coming, and then it is uh, entering inside a nozzle, and this nozzle will have different diameter and different geometry. In the first portion of the nozzle there will be some heating element, and then from this end of the nozzle the melted wire came comes. So this is the wire, but it is kind of pressed or pushed down. This is pinch roller. The pinch roller surface doesn't look like just round or flat round. It has a groove. So how should I make a groove now? The cross section of pinch roller will look like this. So means where the pinch roller is having a groove in its surface, in its periphery. So the rollers are like tires. So now you imagine you are passing one spool of wire to the nozzle. Now if the spool is rotating, if this spool is rotating, the wire will come from the spool, and you imagine there is no pinch roller. The wire is coming directly to the nozzle, and then when it is coming to the nozzle is heating, is having some heating element. So nozzle will heat up the wire, and it will heat up till the wire is like softened. So that softened wire is coming out of the nozzle. It's not fully melted, but it's semi solid, it's semi melted wire. I should write semi melted, almost melted, but not fully melted. So, if we are giving the wire from the spool as it is without any pinch roller, then there is how can the wire come through one pipe all way from spool to the nozzle? There is no guide. Like we have, you have to have a guide roller or guiding element in that path, so that the wire can be pushed, the wire can be pulled. So this thing is like this doesn't rotate solely. So this pinch roller is rotating. So this is rotating like this and this. Okay, so these two are rotating in opposite direction, and when they are rotating, they are pushing the wire, or they are pulling the wire in downward direction. When they are, when this pinch rollers are rotating like this na, they are indirectly pulling this wire in downward direction. So because of their rotation, the wire will come down. When the wire is coming down, it will be heated up because the wire is having high friction with these rollers. This roller's work is to pull down the wire, is to make or build a tension in that wire so that the wire shouldn't get bent in between somewhere where it is coming from the spool to the pinch roller. So there will be a high tension in the wire. So to maintain this tension, high tension in the wire, the pinch roller is used. Also to give a direction and a guide to the wire, the pinch roller is used. And also so that the wire can come all the way from spool to the nozzle directly without having any bend in between or without having any disturbance. These pinch rollers are used. There is no very difficult mechanism in pinch roller. The pinch roller will just move, will just rotate, not move, rotate in its axis. The two rollers will rotate in opposite direction, and if two roller is rotating, the wire will generally pass in between that roller. So this is how the pinch roller works, and this is how the FDM works. Now you ask me your specific question that you could not understood.
Ma'am, what is the specific temperature for a semi-melted wire, ma'am?
Okay, so the thing is, it's different. It's different for different material. For example, there is two temperature. Okay, one is the bed temperature. When this semi-melted metal or semi-melted wire comes, it will have certain temperature, and it will get adhered to the build plate. Now here there is one thing. If you are using polymer build plate, you will lose the build plate very easily because polymer will not be durable. So the build plates are mostly metallic. So the metallic build plate will be heated up first. So there will be a build plate temperature, and there will be the melting temperature or deposition temperature. So in some machine, you will follow that when this pinch roller is pinching, like pulling down the wire, the heat is increased, the temperature is increased in the wire. When it is passing through the nozzle using these heating coils, the wire will get softened, and when it moves through this nozzle end, the nozzle will again have some heater, and it will get melted, like semi melted or almost melted. So this building deposition temperature is different for different material. For example, for PLA it is around 190 or so. For ABS it is around 225 or so. Like for example, for build plate also, if you are using if you are depositing PLA, the build plate temperature will be something around I think 45 or so, and for ABS it will be something around 85 or so. So there is difference in the melting point of each material, and according to that you'll have the deposition temperature and build plate temperature. So I would like to give an example to make you understand the pinch roller mechanism. So did you see the sugar cane juice? How you get the sugar cane juice? If you have seen, then you must have seen that there are two rollers which are moving, and those rollers are having something embedded on their surface, which is like pulling out the sugar cane rods. So one person is providing the sugarcane rods from one end, and from another end the sugarcane rods are fully pushed and the juice is coming out. So the way the rollers rotate, and the sugar canes are like pulled outside, the same way this pinch roller mechanism works. Now you can ask your more doubts, like if you didn't understand this pinch roller and FTM. Can ask.
No doubts, ma'am. I got it.
Okay, okay, got it. Did you have any other doubt in lecture one? Any other confusion?
Ma'am, can I check and say, ma'am?
Yes, yes, sure. In between, uh, I can just briefly mention the other topics, as this lecture video will be uploaded in YouTube also. So if some other students are also listening to it, so they may have some other doubt. So just as a recap of the lectures of week 7, so the FDM process was described, how the extruder works, what is the extruder, what are the parts in a extruder. The extruding mechanism is done using a pinch roller. The pinch roller will have some grooves and how they work. These things were described. Then, obviously, if the wire is coming from the spool and the pinch roller is pulling out the wire by rotating, then there will be a tension in the wire. Now, it should not be the case like the spool is rotating at a high speed than the pinch roller. So, a lot of wire is getting accumulated at the beginning of the pinch roller, and the pinch roller rotation speed is not that much that it can pull out that much of material, then there will be problem. So the velocity of spool and the velocity of the roller rotation and the uh, velocity in which the wire is coming out and coming out from the nozzle, everything should be maintained and should be under control, and there should be one mathematical equation in between them. So there is a flow rate because the material is getting melted and coming out. So the flow rate means volumetric flow rate. Q is speed into area. So by that you one can calculate the flow rate of the material, for example polymer or metal, which comes out of the nozzle, and one can calculate that how much speed the pinch roller should rotate in so that the wire would have a good tension, and also there will be no buckling of the wire. Because if this happens, like the pinch roller is also similarly rotating at a very high speed, that a lot of wire is getting accumulated at the beginning of the nozzle, then again there is a problem. There will be clogging of the nozzle. The nozzle will be clogged and you will not get the deposition. So the deposition not even start. So this is why the flow rate, the speed of each component is very much important, and they are related to each other. They are dependent to each other. No component is independent of each other. So there are some equations. So we have the lecture note. We can follow that as well. Um, Maybe I would mention, because these week's lectures were a bit lengthier, so it will be better if I not write down every equation in these slides and just quickly tell you about the points that has been pointed out in the subsequent lectures.
Ma'am, one doubt, ma'am.
Yes, yes.
What is mean by surface roughness, ma'am?
Surface roughness. So, for example, uh, you are sitting on a table or you are sitting on a chair. So, if you look at the table surface, so this is the table and this is the surface of the table. This thing. Now, if you look at this table in your naked eye, you will not find anything on the surface. Like you'll feel the surface is flat. Now, if you rub your hand over this surface, you'll feel the surface is flat. Okay. But if you see this surface under microscope, you will see the surface is not flat, but the surface is having some undulation in its surface. Like the table is having some undulation like this in its surface. Maybe these undulations are in millimeter, like this thing is in micron or millimeter. Okay, that's why in naked eye you cannot see it. Also, if you rub your hand on the table, you cannot feel it, but under microscope you can see it, because the table surface is always very smooth. But if you touches any rod, like the grills which is present in your window or in your door, that iron grill, if you touch it, you'll not feel that it is very smooth, it is very rough. So it is rough means it has some roughness. Now what is surface roughness? That if your surface look like this, like there is some peak and some valley. Now this is not a graph, this is how your surface look like under microscope. Okay, so this is called a peak and this is called a valley. Now this difference is something, right? Now there is a reference line, that if this is a reference line which is placed over here, so this is the reference line. Means if your sample or your material is perfectly flat, then your material would have the surface like this, completely flat, but it is never possible. Your surface will have some undulation over it. So the undulation can be very large, like in millimeter or centimeter, that you can feel it while you touch it, or you can see the roughness, or you can see if it's very less, like the roughness is in micrometer, like the value of this peak from the reference. This is peak, and the value from the valley. This is valley, rough value. These values are in micron. If then you'll see it under microscope, and this is known by surface roughness. And you calculate the roughness, because while you print something in additive manufacturing, surface roughness is very important. If you are printing one part and it is having very high surface roughness, like the surface, like each surface is not flat completely, each surface is not plain completely, there is some undulation, there is some roughness in it, it will not look better, and you'll not feel confident about that part. You cannot sell that part. If you are making one toy and the toy is not smooth from the upper surface, you cannot sell that toy. So what is the purpose of using additive manufacturing? So surface roughness is a type of output that we get in a particular part printed using any AM process. Now how we calculate it? So there is something called SA, something called RA. What is this thing? So it's like SA means when you take a full area, and over that area there will be some peaks and there will be some valleys in the whole area. Okay, whether you see it or not, that is difference, that is the value of the roughness, but the roughness will be there, some peaks and the some valleys. So these are valleys, like which is going down the reference line. This is peak, which is going up the reference line. So this peak and valley values, if this is peak 1, the value is x1. For the value, the valley, the value is y1. So you'll have some x1 plus x2 plus x3, and then you'll have some y1 plus y2 plus y3. And then if you have n number of peaks and valleys, you divide it by n, so you'll get an average roughness. And that average roughness you are taking from a surface will call as SA. When you are taking RA value, RA means you are taking one line on the surface, like if this is the table, and you are taking one line over this table, and in that line you want to see the surface roughness, then you'll see some roughness like this. And if you take the peak valleys and then values of the valleys, and then you add it and do the average thing, then you will get the surface roughness, which is known as Ra. Then another thing is Rz. There is another thing called Sz. So these are different values of surface roughness depending on how you are measuring the surface roughness. But this is how or what surface roughness means.
Ma'am, they will ask problems related to it, ma'am.
They will make some problem because if I talk about, like as I said, if you are opening a toy industry, so you will obviously make the toys using FDM process. If you are making it in additive manufacturing, then you'll choose FDM process because FDM is very popularly known for polymer printing. So if you are printing using FDM process and you are not getting good surface roughness, then you have to go for some post processing. And if you are going for some post processing, that will cost you more again. So you have to add the cost of additive manufacturing plus post processing. Now the price of each toy has increased so much that nobody will buy it, so your company will not get the profit. So to be in the profit level, you have to print something which will have lesser surface roughness, which will have very smooth surface with accurate geometry, good finishing. So if you are getting the finishing in your additive manufacturing, then you don't have to go for the post processing, so the cost is saved, so you'll get more profit. So this is how you think what is how the surface roughness may affect, because this is true for every company. Like we people do use the metal additive manufacturing. In metal additive manufacturing, there are several studies in which people have just shown that how different process parameters are affecting the surface roughness of in a part quality in a particular material in a particular process. So if you are using LPBF, if you are using DD, if you are using this metal, that metal, then what should be the process parameter, like what should be the laser power, what should be the scan speed, so that you can get the least surface roughness in your printed sample in LPBF. If you are getting the least surface roughness, means that parameter is good. So this type of studies are available in online. So this is how the surface roughness is very important. Anything else?
No, ma'am.
Okay. Uh, okay, then should I move to the slides? Maybe yes.
Yes, ma'am.
Okay, so you have watched the videos till week 1, week 7, lecture 1. So, till lecture 1, what I can see is the pinch roller mechanism was described, that I have cleared your doubt, I feel already. And then there was the nozzle arrangement. How this three zones of a particular nozzle is different was described, and then how the shear force, viscosity, fluidity, everything matters, we know. And there was a problem. This was pretty simple. If you watch the video very carefully, you'll understand most of the things. If you feel any doubt, obviously you can ask me out. In lecture 2, then lecture 2 onwards, there is some other topic. It is related to the wire additive manufacturing only, but some deeper understanding in the material flow. I'll draw something first. Now, as I said, that the spool, at which speed the spool is rotating, at which speed the pinch roller is rotating, at which speed the wire is feeding, like fed from the spool to the pinch roller, at what speed the wire is getting pinched and pulled out of the pinch roller and moving towards the nozzle, at which speed the nozzle is heating, like what is the flow rate of the material inside nozzle. Everything is very important, and everything is interdependent or intradependent. Now, like that, this material which is now coming out of the nozzle, now that material will get deposited over the build plate. So there is a build plate, and uh, one second, something. So if there is a build plate and now the nozzle, from the nozzle the melted material is coming, then what should be the placement of the build plate down to the nozzle. So if there is the nozzle end like this and this build plate is like this, so this is the distance between the nozzle and the build plate. So if this is the distance between nozzle and build plate, then how much should be the distance? Now someone may say that you increase the distance. How this is very important. You can take any distance between nozzle and build plate. I would say no. This is not true. Because first you think when the material is coming out of the nozzle, it is almost melted. Now if you keep this distance really very high, then um, your melted material should first come onto the build plate and it should have solidified properly. And at the time of solidification, it should have bonded, or it should get bonded with the build plate. That is also important for the first few layers. So if now this is three study that is going on inside that deposition, then if you increase the length, the distance between nozzle end and build plate, it may happen that in between when the melted wire is coming, it will get solidified because there is ambient temperature in the environment. The process is not that much controlled. No air or argon gas or any other gas is flowed over the process, so it's taking place as ambient temperature. So obviously the melted wire is not having very high temperature like metals. So if they are having very low temperature like 150 or 190 degrees centigrade, while the material is coming over the build plate, it may get solidified, or it. Somebody has come. So if now you increase the distance, another thing may happen, which is like if like how should I say? Uh, okay, the melted wire is looking like a cylindrical beam like this. Now, if you increase this distance very high, like you are increasing a lot, then when the melted metal will come onto the build plate, it will look like this. It will get thin. So there will be a thinning in the wire, thinning in the melt pool, or thinning in the melt wire. Obviously, because you have increased the distance very high. So that should not be the case, because depending upon the width, thickness of the melted wire, you will have the layer thickness, you will have the um, area, you will have the quality of the part. you'll have the accuracy of the part, and also you will have the surface roughness of the part. So now if we are deviating from the actual width or actual diameter so high, then obviously your purpose will not be served, so you cannot make the distance between these two things very high. Now again, if you make a very less distance between this nozzle end and the surface, now if this distance is really very very low, then lot of material will get accumulated like this. So the material should come like this and deposit over the melt pool like this, and it will get melted like this. The nozzle is moving in this direction, so it has deposited a very uniform layer of melt. But here this distance is good, but if you decrease the distance, then a lot of material will get accumulated at the build plate. So that should not be the case again. So that's why you should have an optimal distance between nozzle tip and surface, and which is called stand up distance. So in any additive manufacturing or in any manufacturing process, conventional ho या फिर unconventional ho, if somebody is telling you that what is the stand up distance in this, so you assume stand up distance means the distance between the build plate over which the operation will take place and the nozzle or the tool, main tool which is serving the purpose, which is doing the manufacturing. Okay, so this stand up distance is one process parameter. So I have added more information about this stand up distance than the lecture, because anyway you will watch the lecture, so you will get the idea about those things. So that's why I want to just add some more points so that you will have multiple knowledge on the same topic. So then professor has discussed that how the melt wire can have a bulge when it is coming out of the nozzle, because when it will come, like all on a sudden the wire was of solidified thing and now it is getting melted and coming out of it. So because of the viscosity, it will look like this and then it will deposit like this. So there will be an expansion of the liquid, because it was inside the wire and suddenly it is coming in the air pressure, in the ambient pressure. So obviously there will be an expansion of the liquid or melted wire. So because of that, you may have some distortion. Excuse me. You may have some distortion in your part if your stand off distance is really very low. So that's why the process parameter, along with the process parameter of stand up distance, this nozzle opening diameter is also one parameter. Depending upon this d or this diameter, you will have this d. So if this is d3 and this is d2, then depending upon d3, you will get the d2. And if your d2 is really very high than d3, then that is not good. You should have a lesser value of d2. So d2 should be lesser than d3, but you often get d2 more than d3. So there is a relationship between these. So there is a term which is used as die swelling. Swelling हो रहा है इधर. So the melted portion is getting expanded, it is getting some swelling. So that's why it is called die swelling. And there is one ratio of die swelling which is known as S, and S is equal to D2 by D3. And this D2 by D3, as it will be always like S greater than 1, so it will be always greater than 1. If it's not greater than 1, then it means that the melted wire is not having much elastic energy stored inside it. So that's why it is not getting expanded. So it is not good. It should be expanded a little bit, not more than a optimal value. So this is the knowledge out of it. So now one thing is like the stand up distance, as I said. So along with the stand up distance, there is directly connected another parameter, which is like the flow rate of the melted wire coming out of the nozzle. So if you are giving very high velocity to the melt wire, then the melt will come out of the nozzle very fast. And like, if your feeding rate, let's understand the process parameter of this process. So one is the feeding rate of the wire. So this pinch roller is rotating. So this pinch roller rotation will be one parameter. Let's understand like this. Depending upon that, you will have the spool rotation, which is second. So this is dependent. So this will not be considered as a process parameter. So the spool rotation should be dependent upon the pinch roller rotation, and it should be in such a way that there will be a tension in the wire between spool and the pinch roller. The second process parameter is, now the pinch from the pinch roller the wire is coming to the nozzle. Nozzle is having 2 3 region, and now at how much speed this pinch roller is rotating, that depending upon that, the flow rate of the wire will be defined. Now from the nozzle, like nozzle is like a head in which the pinch roller is mounted. So this is the head of the FDM process, like head of FDM process, FDM head you can call it. So this FDM head consists of these many things. So the head will now move in X or Y direction or Z direction also. So when it is moving in X and Y direction, that is called as the speed of the printing or deposition speed. At what speed this head is moving in X and Y direction to deposit the material. So if this wire is moving really fast, if this head is moving really fast, then your deposition speed is fast. So if you do not have sufficient melt wire coming out of the nozzle, then that high speed will result in a thinner deposition width. When you'll get thinner deposition width, I repeat, when you are moving your head at a very high speed, but the melted metal or melted polymer which is coming out of the nozzle is not enough to get deposited over the build plate. So this thing will happen over the build plate. Like this is the nozzle, this much volume of material should come, but it is moving in so high speed that it is getting thin, and this is thinner width of the track. Okay, so this is one case. Now if you are having a very low speed, then the wire will get accumulated and you'll get like this is the head, this should be the track, and you're getting a wider space. This is also not uh, accepted. So we want something like, it will move like this, it will deposit like this. So this is the accepted, this is not accepted, this is not accepted. So the deposition head movement speed is also important. When the distance, like the stand up distance, is really low, or the nozzle head area is also one factor. This area is not appropriate. if this is the, so this is having area 1 and this is h. So ideally this area 1 should be h square by pi. So if we are not fulfilling this criteria, you may have thinner deposition or wider deposition, depends. So if the standoff height is very low and the speed is very high, then we get some shape like this. And if we are really getting one bead shape like this instead of this, then it is called as oblong shape. So this is the overall understanding behind the process, how it works. Now there is another factor. When two bead is getting deposited, so this is one bead and this is next bead, and they are having some overlap with each other, obviously, because one bead should be properly fused with the other bead, and if you really want that fusion, then you have to have an adequate overlapping. So if you are not getting that enough overlapping between each other, then your bonds will not be strong. So also, when you solidify this melted beads with overlapping, they will form some neck like this. So this is two bead number 1 and bead number 2. And in second step, necking will take place between these two beads. And after that, you'll get a bead like this. So if you are getting beads like this, then this is the ideal. But every time you cannot get bead like this, so you get a bead like this, a little undulation in the beat. This is also accepted. So this is the overlapping, the working of it, and how the neck formation take place. It is called necking. So it's basically the neck formation in the beat. Again, there are some heat transfer equation and heat transfer model in which you can get the optimal speed of the nozzle head, you can get the optimal volumetric flow rate, you can get the pinch roller movement, rotation speed, the spool wire spool rotation speed, the speed between the wire which is coming out of the pinch roller and going inside the nozzle head, the distance between these two, everything is optimized. That then only you can make a printer, or you can make the machine which can efficiently print the part. So if you are having optimized parameter of all the things that I said, then only your machine will be able to print something. So you have different parts, and you have different heat transfer model for each case. And if you when you'll watch the videos, you'll get to know those equations, because time is very less in this doubt clearing session, so I cannot go through each parameter and each model here. So I'm just overally talking about the topic. So till now, if you have any doubt, you can ask me.
No doubts, ma'am.
No doubt. Okay. Okay. Now I will move to the notes. Is my screen visible?
Yes, ma'am.
So this is the wire-based additive manufacturing that I'm talking about. So this wire-based AM slide is visible, right?
Yes, ma'am.
in the PPT. So this is the PPT that you guys also have with you. This is the PPT given by professor. So and then fuse deposition modeling is using the polymer, composite, metal, every material. Now the material flow is very continuous. Like continuously the metal wire is getting melted and deposited over the build plate. The head is moving onto the build plate so that your continuously coming melted wire can make the desired geometry. Then the machine kinematics, like I have told in last to last class, that there is subcategory in each AM, like the manipulator, machine, material delivery system, heat source, and heat source delivery system. So that manipulator, like machine kinematics, is serial. Like you will have motorized connection in the bed. You will have the motorized connection in the nozzle head and build plate. So the build plate may move in X and Y direction, and your nozzle head will be mounted over a, CNC or over a just normal, very simple motor. The motor, if the motor runs, you will have the movement in the build plate in X and Y, and you'll have movement of the nozzle head in Z. Very normal configuration. So this is called known as serial kinematics. If you are having parallel kinematics, then there will be manipulator like robotic arms. So this robotic arms will have more degree of freedom in one movement. Like even if it's capable of moving in direction, it will also be capable of moving in X and Y direction along with Z. So there will be combination of this, so the degree of freedom will be more. And hybrid means your build plate is like having the serial kinematics and your nozzle is having the parallel kinematics. So that is the combination of both you can one can use and get. So the energy source is here resistance, because you don't use any laser, you don't use any plasma, you don't use any arc or electron beam which is coming and interacting with the material. No such high energy source is used. Only you use some resistance coil. The coils do heat up because of the resistance, like they are coiled, metal wire is coiled, a conductive metal wire, so obviously that is a kind of resistance heating. When we pass the electricity in the coil, they get heated up and they heat up the metal or polymer wire, and you get the melted wire. Then support structure is written as water soluble. So it is not always true. You will have FDM machines which are capable of printing only one material. If they are capable of printing only one material, then you have to print the support and the part with the same material. Then it is not a water soluble support. But if we are having multiple nozzle in one printing, and if multiple wires, like different wires can come simultaneously in that two nozzle, then it's better. You will have, you can print the support with a cheaper material, then you can optimize the cost of the process. Or otherwise, if you print another material which is water soluble, then again you don't have to go for any post processing. You just dip the part in water and your support will be dissolved. You'll remove the support very easily. So this is the thing. So then you have your machine. So this is the pinch roller. So this pinch roller, and this pinch roller is rotating like this. Okay. And as they are rotating, the wire is pulled down. This is the nozzle head. It will have the heating element, and you are having the melted wire. Then there are some this is the groove that I was talking about. So if your pinch roller is having, if your
Ma'am,
pinch
what
roller,
material there? Ma'am, one doubt, ma'am.
Huh, yes.
What material they are using in groove, ma'am?
Groove. Okay, these are just normal steel or just metallic pinch rollers. Not very like something different. Just normal metallic. I don't know the exact metal, but I feel you can use steel, stainless steel.
Okay, ma'am.
Okay. So if you are having this groove, so there is an advantage of using groove. So if you are just using normal pinch roller, then it will somewhat look like the tires, the car tires. Now you imagine if you want to push two tires together to make the wire pulled in downward, then the contact between the wire and the uh, tire will be line, and line contact you can have slip in that line contact, and it will not be very much efficient. Like in one line you'll be pressing the wire, and in another portion you'll not press the wire. So this is not a good situation. So that's why we make a groove in the pinch roller, so that you can increase the surface area of the pinch roller which is coming in contact with the wire. Then, as I said, this is the flow rate of the material which is coming out. So, these are the equations. If you go through the notes, you'll see the force which is responsible to pull out the material, the pressure which is they are present because of the pinch rolling mechanism, the tension, everything is dependent with each other. And as the wire is pushed downward, there will be some shear deformation, shear force acting on it. And if the shear force is causing any deformation, then that is called as shear deformation. Now you imagine if you are giving a very high pressure, high force to the pinch roller, you will squeeze the wire in between. And if you are squeezing the wire, that is not good. Again, you have to just push the wire in such a way wire may have reduced the diameter, but it will not be squeezed, it may get broken. Okay, so that pressure is also very important. And also, as I said, if your speed of the pinch roller is not optimal with the length between distance between pinch roller and nozzle, you can have buckling of the wire in between pinch roller and nozzle. So these are the equation of buckling. You can see like different mechanism of buckling. The only thing you need to know is there can be possible buckling in the wire if this LF length and this force which is given to the wire because of this pinch roller movement are not optimal. Mm. Then there is some stress strain relationship in the wire. Obviously, you if you read this note, you'll understand for sure. So the second note, if I go through, this is the thing which was I was talking about this thing. So if you are having the nozzle diameter as D2, and if you are having, so I have denoted the D2 and D3 opposite. So you can denote it either, whatever you feel. You have to just write the equation right. That is what important. So if your nozzle opening is D2 and the expanded die swelling diameter is D3, then D3 by D2 is the swelling ratio. And this swelling ratio is always as like greater than 1. It should not be less than 1. But it should not be very much greater than 1. It should be
Ma'am,
between
one
1.
doubt.
Yes. Yes.
What happens when D2 value is greater than D3, ma'am?
Okay, so if your D2 value is D2 means this. So if your D2 value will always be lesser than D3. Okay.
Okay, ma'am.
Because you okay, so if the wire is coming in the nozzle, now you imagine in the whole path, in the pinch roller, from pinch roller you are pushing the material, you are pushing the wire in the downward direction. So you are making some tension with the spool material, you are building some shear force inside the material, but again you are not letting the wire get deformed. So the shear stress is now present inside the wire because you have applied force but didn't let the wire expand, contracted. So if you have applied the force, if it is contracted, then it is not having that stress. But if you have given the force and it is not contracted, then the stress is more. Okay, so if you have developed a shear stress inside it, which is in elastic region, which is not in plastic region, if you are getting some deformation in your wire, that is in plastic region. You know the normal stress strain graph, right? So where is my pen? If you are having this graph, and in this graph, this is Hooke's law. This is the like the upper yield point, lower yield point, and then plastic region starts. From until this portion, this is elastic region. This portion is fully plastic region. So now you have applied some force but didn't let the wire get deformed. So obviously you are in elastic region. And now you have developed some shear stress inside the material as that didn't get deformed. Now you are again putting that wire with a lot of tension and shear stress inside the nozzle. Now the nozzle is having some heating element. You are again exciting the wire atoms and you are getting some melting in the wire. So there persists the elastic force. The elastic force is still persisted inside the metal wire. And now finally it is coming out of the nozzle. So it is now finally relaxed. Of bach gaya hum. Like that. Okay. Now if it is coming out of the nozzle, it is getting relaxed. So now it will release the shear stress which was built inside it previously. So if it is relaxing or it is releasing that elastic force, like which was stored inside the wire as elastic energy. So if it is releasing the elastic energy, it will get expanded. Obviously it is releasing the force. So then you will get the D3 more than D2 always. The elastic stored energy, because of the elastically stored energy, you'll get the expansion in the metal or the polymer wire which is coming out of the nozzle. So that's why D3 is always greater than D2 and you'll get the S value more than 1. Now what happens if the S value is lesser than 1? That means there can be few possibilities. So if you are not getting D3 more than D2, means the elastic energy is not stored inside the wire. If the elastic energy is not stored inside the metal, then something, obviously something has happened wrong with the metal wire, with the polymer wire, because the way I have discussed till now, you are now I think having some idea that it has to have that elastic energy because it is having the tension, it is having the shear deformation, it is having the shear stress, like all those things. So now if it is not having the shear stress inside it, it is not having the elastic energy stored inside it, that means maybe the wire has come alone. matlab, the wire has come alone inside the nozzle. The pinch roller stress was not enough to pull down the wire. So in actual, the pinch roller pressure has not been applied over the wire. The wire has come down to the nozzle without any support, without any guide. Like the pinch roller was rotating, but the pinch roller rotation was not responsible for the wire movement. The spool was rotating, that's why the wire has come down by chance. So by chance the length between each element was so optimal that the wire has come down to nozzle and now it is getting melted and deposited, but the pinch roller has not served its purpose. So that's why, as the pinch roller has not pushed the wire, it has not developed any shear force inside it, so the elastic energy is not stored inside it. So which is wrong, which is not be the case. So that's why die swelling is good, but the swelling ratio should be in a limited range. Otherwise, it will distort your printing quality. Okay. If you have any other doubt, you can ask. Or if you have understood this concept, you can tell me. Or if you have not, then also you can tell me.
No, ma'am.
Okay. Then as I said, the flow rate of the wire which is going inside the nozzle is important. Like the same way, the flow rate of the wire which is coming out of the nozzle is also important. So you'll have certain equation on that as well. Then the phenomena that I have described, that this is A1 and then there is a speed, and this A1 should be minimum value of this A1 should be h square by pi. Otherwise, you'll get that oblong shape. So this motion of the print head is also one parameter. Like the way you are depositing, if you are depositing really high speed, at a very high speed, then maybe you are not giving enough time to the belted wire to fall down over the build plate. So you'll get thinner width. And if you're giving very less speed, then you can get some accumulated heat over the build plate. So you have to have the optimal one. Apart from that, in any other way, if you are depositing in optimal condition also, but if your layer thickness is very high, then you'll get some distortion over your bead. So in that case, the nozzle will not deposit the wire from far away. Rather than, the nozzle will deposit in such a way that when the bead is deposited, the nozzle will touch the upper surface of the bead. So if it touches the bead, then it will iron the bead upper surface, and you'll get a flat bead, so your surface roughness will be lesser. So this bead ironing is one technique where the nozzle touches the bead and deposits it. Then there is the neck formation and final growth and fusion of the beads. There is one thing that it is assumed that the bead will be elliptical in nature. So that's why the equation of the ellipse is given in this slide. And then you'll find that if a bead is depositing, then obviously there is a trailing edge and there is a leading edge. Leading edge means the point or the edge where the nozzle is depositing the material, and the trailing edge is where the nozzle has already deposited the material, a solidified portion. So in the trailing edge and leading edge, there will be a temperature difference. So if you consider the temperature difference in your heat transfer model, then you will get the optimal flow rate of the material which is coming out of the nozzle, and the viscosity, surface tension of the liquid is also very important in this case. So you can see these equations, you can just rewrite the equation and you'll understand it while you'll see the video. Again, there is the cross section of the material, like how the material will come Like if you increase the speed, if the velocity is not constant, if the velocity is very less, if it's very high, you'll get different types of beats. And you always need a flat beat, so obviously you'll go with the optimized parameter. So then comes the staircase effect. Staircase effect is seen in almost every kind of solid additive manufacturing technique, because you can't see this staircase effect in liquid additive, because in liquid additive you cannot see the layers after formation of a particular part, because it's so fine fine surface process, so obviously. But in solid additive, any solid additive which is a layer by layer process, you'll see the staircase effect. Why? When you deposit a slanted wall, so the layer is, I'll draw it. So the layer is spreading like this, and if you want to build this thing, so obviously the next layer will be somewhat lesser in length, the next layer will be lesser in length, but these beads will be almost like rectangular kind of. So that's why if we are not having a very thin layer thickness, if your layer thickness is not very thin, then you'll get distinguishable staircase effect in your part. Now in that case, it's recommended that you lower down your layer thickness. You can avoid this issue. This is the surface roughness you have already asked. So this is how you can calculate the surface roughness. Then the next process come, which is the another classification, which also comes under FDM, but where we use the parallel kinematics. So there is one video, like this tool. This is the nozzle head, okay, and this nozzle head is connected in these two fixed beams. So this is fixed and this is movable. So these and these both are movable. So these two will simultaneously move. So this head can move in X and Z position simultaneously. Like in normal, in serial kinematics, if you have to go from this point to this point, then the nozzle will move like this, but the CNC controller, how it is like attached with it, it will move like this. Okay, first in this direction, then in this direction, then will reach from this point to this point. But here, the connection, the manipulator is in such a way that you can deposit in any position simultaneously. Okay, so the deposition rate is also high, and hybrid is the combination of serial and parallel kinematics. Then comes the drop on demand. So in FDM, we mostly see the continuous building process. So if the building process is continuous, then continuously the melted wire is coming. But if it is drop on demand, then over the build plate, the head will move and it will deposit the material in drop by drop. And the drop will come only when it is needed. Like drop by drop, it will move and deposit the material, and where it is not needed, it will not deposit. So this is one thing. And then let's go to the lecture 7, sorry, lecture 3 of week 7, which is the last lecture. It is not opening. Yes. So this is what is different from the last two lectures. So if you have any doubt, you can ask me. No doubt. Okay. So now in metal additive manufacturing process, like in all other additive manufacturing process, what I have found out is that I knew vat polymerization is the first process in picture. But after going through this lecture, I got to know that the patent on metal wire additive manufacturing came before the the patent was filed even before the vat photopolymerization. So it is really very old, and this concept was actually came from the concept of welding. So, metal wire additive manufacturing. So, this is the history. Like a brake drum was worn out, and using the TIG MIG welding, the brake drum was rotating, and the filler, like in TIG welding, it was uh, redeposited over the material was redeposited over the brake drum, and the brake drum was corrected. So this is how this that is a kind of cladding process of metal wire, and the patent was filed even before vat photopolymerization. So there are also other evidence of other patents of different metal wire additive manufacturing process. Some people have used the concept of cladding using metal wire. Some people have used different heating source. Some people have used arcs. Some people have used flames. Some people have used MIG welding. Some has used stick welding. So using the basically the using the concept of welding, they have developed this system. Now apart this TIG MIG welding is different. So you can just go through this lecture, you'll understand these are simple things. What is very different from these things is shape deposition manufacturing. This I also have found out very interesting. So shape deposition manufacturing is also additive manufacturing process. But one thing you understand is additive manufacturing process is known as layer by layer material deposition process. Why? Because the slicing we do before putting the CAD file inside the printer, the slicing file defines each layer thickness. And this is how in slicing we define each layer. And depending upon that slicing, the printer prints the part. So this is why this is a layer by layer manufacturing process. In shape deposition manufacturing, we do not give the slicing file as layer by layer information. The slicing file contains volume information. Like the slicing file will not define each layer thickness, it will define certain volumes. So, how? If you read out this lines, you will not understand anything. Let's understand the thing like these are the different processes of shape deposition modeling, like using TIG and MIG. Let me just draw this thing, then maybe it will be easy. Let's understand. If you are printing it, this is the part, okay? This is the whole part. So, in this part, this is the support. This blue portion is the support, and this yellow portion is the part. Now, when you're printing like this, you do not you need the support structure because the blue part is the support structure. So you'll start with the support structure and then comes with the part. When you're printing this profile until this point, there is only support structure. So this shape deposition modeling says that you need the slicing only when there is a distinct um, distinct difference of building the support, or there is distinct difference in the part. So until this point only support is getting printed. Okay, now again when you reach this part, you feel that this part can be printed without support. Okay, so until this part you have two nozzles. So one nozzle will deposit this blue part and one nozzle will deposit this yellow part. So you'll get a slicing here. Then next, when you go till this part, this is 1, this is 2, then you will see that you will get the support and the metal, but this thing needs to have the support. So this will print the support, this will print the part, here support, here part, here support. Then again, the things are similar. When you reach this part, again there is a change in the slant, so the support is changing. Like, if I don't know whether I am understandable or not. The thing is, whenever you feel there is a change in the geometry, you will slice it, and until that you'll deposit it volume by volume. Maybe this part will be better understandable. So you are printing this green part, okay? And this yellow is support. When you are printing the first part, you don't need the support. You can print the part solely. So you will print the part 1. Then when you'll go until this portion now, you will have a slant in this direction, and this slant needs the support. So now you will print the support. You start printing the support. So after this slice, you'll print the support of 6 and 5 region. Then till this point. Then again, this portion is different. So when the fifth part is printed, sixth part is printed, you'll print the part 2. After printing the part 2, you'll print the part 3 or 7, and then you'll print the part 4. So this is how you do the slicing of each volume wherever there is a distinct difference in the support or the part, and you do not give the printer as the layer by layer information. So there is again another very interesting topic of geometric processing of for SDM. What is that? So in geometric processing, you divide a particular part into few portion. Like for example, this part, I will divide it in few portion. Until this portion, this is going like this, and then again change in the geometry. So I'll cut down the feature from this, from this. So now I'll print the parts. So obviously I'll have the support here. So now if I make one, like here, if you see 1, 2, 3. So here it is 2, here it is 3. So then here it is 4, 5, 6. No, this is not 6 because, okay, sorry. This is not 6 because this whole part is will be 4. This is 5 and this is 6. Okay, the vice versa. So now, if you see this part, this sixth part is not really required. You do not need any support. This is slanting in downward direction. You don't need any support. And this is completely perpendicular to the flat plane. So you do not need any support. You cancel this part. Okay, this go to the trash. You don't need this to print this part. This part, 5 part is needed because this slanted wall needs the support. Okay, now this wall doesn't need the support, doesn't need the support, but this wall needs the support. If this wall needs the support, then obviously you have to print the support throughout the fill plane. So 4 is needed. So now this software, like this deposition process, make the series of the deposition, like the way your part should be deposited. So it should be like, first, one part will be printed and you make a flow chart. Then, when one part is printed, you need the support in fifth part. So you cannot start with part 1. So what you start with the part 4, where I have written it at part 5. So you start the printing with part 5. Then when part 5 is printed, you now can print part 1. So you print part 1 and you print part 4 also. So one nozzle can print part 1 and one nozzle can print part 4. Now when part 1 is printed, now you can print part 2, and as part 4 is already printed, so now you can also print the part 3 because the support is printed. So there can be interlinked like after which part should be printed, but you have to have one geometry. So that's why you first print this 4, then print 1, then print 2, sorry, then print yes, for after 1 you can print 2 also. Okay, then for 3 you need to have the support, so it's better to print 5 first and then you print 2 and then you print 3. So this will be the order of the printing. So this is kind of a slicing dependent upon the volume of the part. So is it understandable, like to some extent? Because when you'll be seeing watching the videos it will be more understandable. So is it clear to some extent?
Yes, ma'am.
Okay, good. So this is what was covered. So this is the process how the parts will get printed. So this is the part, this is the support, this is the part, then support is printed, then part is printed, then last part is printed, and you get the final geometry. So this is what was covered in week 7 lectures. Now I have the PPT with me where I have, so I was noting down some slides. So I have the previous year questions. So now we can directly jump to the previous year question and we can see how they were solved, so that you will have easiness in attempting this year quiz questions. So this will be this is kind of a benefit of to have the previous year question solved solution. Okay, no, what is this slide is not going. Okay, yes. So first question is, as you have not watched the video, so maybe I'll discuss the answer. Okay, I will not ask the answer from you guys. So for a given stand-up distance H, the minimum possible area AB mean of the deposited layer in a fused deposition modeling is this thing. Like this is the nozzle, and if this is the bead to be printed like A and this is H. So as I have already told you that the answer will be A equal to H square by pi. So this AB minimum or A minimum should be this thing so that you don't have this oblong shape or you don't have this thinner wall. You'll have a perfect shape. Then which of the following statement accurately defines bead ironing in FDM? The correct answer is the contact between the nozzle outlet and the freshly deposited bead. So the nozzle outlet will touch the bead and iron it while depositing the bead also. Then you have the question. Okay, there is a misorder. No problem. Select the correct statement made within the context of shape deposited manufacturing. So adjacency graph identifies the neighboring segments and minimal precedence graph provides the build sequence. So I have not discussed about this graph. So when you go through the lecture, you'll see like how you will plan the deposition process. What I have shown you in one example, that is what is given in adjacency graph and the precedence graph. The following feature of the SDM process, shape deposition manufacturing process, makes the fabricated part free from staircase effect. So segmenting the part based on the visibility of build and support material or structure. Like in simple words, you just decrease the layer thickness, and you don't decrease the layer thickness in whole part, like you decrease the layer thickness wherever it is needed. So you just segment the part where the support is needed, when there only you put the support, and you segment the part in such a way that you'll not have the staircase effect, because you'll print the volume apart from the layer. And if you are printing layer, you just lower down the layer thickness. So typical thermoplastic material used in FDM exhibit shear thinning behavior, like because of the shear stress which is developed inside the material, you will have the shear thinning while depositing the material, while coming out of the nozzle. For FDM, so this is the KF which is there in heat transfer equation, so I have not discussed. Then in FDM, the nature of force acting on the filament between the pinch roller and the liquefier is compression, obviously. Under the over Under and over deposition of the thermoplastic material using star and finish of the single bead in FDM process can be attributed to the acceleration and deceleration of the print head during start and stop respectively. So it's like, if you are printing, for example, this path, so you'll start at this position. So whenever you're starting one motor, you'll be having one inertia of the motor, inertia which is related to the motor. And because of that inertia, you may have some disturbance in your printing. So if you are having some inertia, because of that, if the melt is coming, so maybe the melt will start depositing from this point. So until this point, there is no bead. You have started printing. You have gone here. So now the melt is coming in this. You will not have the bead here. And again, when you are moving like this, so the head is moving like this, and now head is moving like this. So when it is taking one turn, now you imagine, I can draw it over the slide. So that's why I'm telling you to imagine. When you are taking the turn will be very sharp turn, like go to the x-axis and then go to the y-axis. But the depositing material, which is semi-solid, which is almost melted, that cannot have a very sharp turn. That will have a round turn, like that will be depositing over the build plate, and the moment you will turn your nozzle head, the material will not get deposited at that corner. So if your nozzle head is turning like this, your deposited material will turn like this. And in this portion, there will be no bead. And also, you'll have some thick build here and some thin build here. Thin, thin. Okay, so this should not be the case. So that's why you have to decelerate when you start and stop. Okay, and you have to accelerate when you like start the process, because if you keep your speed very slow, then you'll print some accumulated bead here. So you can have not the acceleration but the optimal speed here. But when you stop the process, when you turn in between, there you do some deceleration, so you lower down your speed, so that properly with the bead which is coming, it can get deposited over the bed. And then you turn slowly, so the bead will also turn like this. It will get deposited like otherwise it will get deposited like this, and here it will be no bead. So you get the turn very slowly, and then when you're stopping the process also, maybe you're stopping the process here, but your bead will stop at here, like you're stopping at here. So there will be no bead again. So that's why the acceleration, deceleration in between the process is very, very important. You cannot print a complex geometry with the constant speed of the nozzle. So, next question is, in the FDM process, the maximum diameter of the extruded material is 1 mm. So this is one numerical. I have not discussed it. So this is one, and the diameter of the opening. So DP printing nozzle diameter is 0.9. So obviously it will be 1 by zero point 0.9, which is 1.11. So this will be the correct option. Then for a given layer thickness of 1 mm, TL is layer thickness, width of 2 mm, traverse speed of 50 millimeter per second, what will be the flow rate? So flow rate is equal to AV. So it should be 1 into 2 into 50. So it should be 100. Yes. That's it. Then the next question is the micro casting process of SDM. So micro casting, because a small segment you are casting, like you are printing it in a volume, and casting is a volume based manufacturing. So that's why it's called as micro casting. So in which substrate needs to be what? So the micro casting process of STM is a welding process in which substrate need not to be electrode, because the electrode releases, so the substrate should not release any material. So substrate should have the deposition over it, and it should be fused. Just that. That's it. Two filaments of A and B diameter is having 3 millimeter and 4 millimeter respectively of the same material. Effective length is to be printed using FDM process. Calculate the ratio of critical force. So critical force is also one thing you'll see in the lecture video in the numericals. So I will tell you the relationship between PA and PD. This is this. So if this is like this, so 3 by 4 whole square. So it's like 3 square by 4 square. So it will come around 0.56. Then in FDM process, the bead ironing results in more stable flow and ensuring flat load surface. In SDM, if stainless steel is used as main material, then copper can be used as a support material. So this is one thing, like stainless steel and copper can have their bonding. So that is more like the material engineering thing, not related to FDM process. Which of the following FDM like process works on drop on demand? So this is on company Airbag who produces this drop on demand FDM process. In FDM process, the standoff distance is increased 4 times, then obtain. Okay, this is again one equation, then nothing else, just the square of it. So instead of slicing, shape deposition do the segmentation of each volume. Which of the following FDM process is hybrid kinematics? So it's kappa. Then we have our last question, which is in the context of FDM, graph, which graph represents the relationship between mass flow rate and viscosity? So it is this graph, and that's about it. Okay, one more question. This is very interesting. So it will be better if you have understood what was there in today's doubt clearing session, then you may answer this question. I'm not sure. So let's try to answer the question. So this is the A that I am interested to print. Inside this A, you will have the support structure, obviously. Those, so the segmentation of A is done. The segmentation of the support needed in A is also done. You have to just order it. So can you tell me what which should be the first volume to be printed among this 1 to 8?
Ma'am, is it 8?
Yes. So it should be 8 because other than 8, 1 and 2 cannot be printed. So after 8, what should be the next thing?
1, ma'am.
Yes, 1 or 2, anyone. And then if I match the option, then obviously it should be 3. Now again, next question, after 3, which should be printed?
7, ma'am.
Yes. So apart, like if you're not printing 7, then you cannot print 4 and 5. So obviously you'll print 7 and then you'll print 4 or 5 together, and then lastly you print the 6. So this is what I have for today. So if you have any other question, you may ask me, or if you want to discuss any other topic, you can also ask me because we have some time left. Otherwise, we can just stop the session.
You can clear doubts from previous assignment also, ma'am.
Yeah, yeah, sure. You can ask. Assignment. Okay. Yes, switched out.
In assignment 2, second sum, ma'am.
Second assignment.
Yeah, ma'am.
Okay, okay, okay. I have to find it out. You can ask me the question, I think. You can ask me the question that you are having.
Okay, ma'am. In the context of using the telecentric lens,
Okay,
which if the following is true,
okay. Maybe I
option
can the question here. I can see it if I have it here. I think I don't have. Yeah, you can ask me. Options are
option A, the
hmm.
scannable area does not depend on size of lens.
Okay. Next.
Option B, it facilitates normal incident of laser beam into the target plane. They are asking which of the statement is true, ma'am.
Okay. Hello. I didn't listen the option 2 and 3. Can you repeat it?
Option B, it facilitates normal incident of laser beam into the target plane.
This is true. Then the third
No, ma'am.
option.
Only two options, ma'am. No third option at all.
Okay. First option is it doesn't that okay. The second option is true that it facilitates with the normal incident. So then option 1 should be the wrong thing. Now what is the answer? Actual answer. Do you have it?
Yes, ma'am. A1 is false and B is true, ma'am.
C1 is true. Yes. So what is your doubt in that? You can ask me. Hello.
I think it is independent on size of lens, ma'am. That
Okay. The
area.
thing is, if you use flat filled lens, you will have the focus spot. If you draw the path of the focus, it will be an arc. So you have to have a flat focus. So there, that is why you use f theta lens. Okay, that is why you use flat filled lens. Now in flat filled lens, if you increase, like if you vary the speed of the laser beam onto the bill plate, the speed of the galvo scanner is different, so you may have vibration in that. So that's why we use f theta lens. In f theta lens, the relationship is like h equal to f theta. So that's why if you use the theta, like if you use h, so if vary the if you vary the point of the laser beam over the build plate in one speed, the same speed you'll get in the galvo scanner, so you'll not get any extra vibration in the galvo scanner. But again, by f theta lens, the build volume is restricted. And also when you increase the um, like what should I say, if you increase the distance between lens, now you'll get some uh, elliptical shape in the flat filled lens. So then it is not desirable because you'll decrease the energy density. So that's why you use telecentric lens. What does telecentric lens do? It does, like, it makes the laser beam fall over the bill plate at 90-degree. Wherever it is falling, the laser beam, it will fall at 90-degree. So if it is falling at 90-degree, then the laser spot will be circular. You'll get a constant energy density, because in metal additive manufacturing, the energy density is one of the most important parameter, and you don't have to be playful with that. You can be playful with that, but you should not play with the energy density, like spot diameter, where you want a constant energy density throughout the printing. That's why telecentric lens is useful where you need the 90-degree, but it's not true that it is restricting the bill volume. It doesn't. You understand the utility of these three lenses?
Yes, ma'am. Another
Okay.
one, ma'am.
Yes, yes.
Assignment two, fourth question, ma'am.
Okay. You asked me the question. I don't have the question there.
In the context of a 3D system, SLA process,
3D system SLA. Okay. I don't remember the company names and their process, but you can ask it.
the gap between the doctor blade, or it is known as sweeping blade, ma'am,
Okay.
and the pre-built layer is 10 micrometer.
Okay.
What will be the obtained thickness of the layer?
Okay. I don't have the form. I don't remember the formula of it. So I have to have the formula of it. So if I can find out somehow the question, then I can have the formula of it. It is from assignment 2.
Yeah, ma'am.
Okay, this question is surprisingly not here in previous year. So that's why I don't have the formula written. So I don't remember the formulas. I can only make you understand the concept. So you couldn't find out it in your notes? Maybe I can find it in my notes.
Ma'am, only that assignment 2 alone, I have scored very less mark, ma'am. So that
Okay, okay, okay. Okay. I really am not sure about the formula, so I have to find it out some way. Ah, not here. Dr. Blade means it's a very old lecture. So I have noted down the formulas because I don't remember those, but right now I cannot find it. Uh, mm, Maybe you can also find it out in your notes. Do you have any notes?
Yeah, ma'am, but I can't able to get it, ma'am. So that only I'm asking you.
Okay, 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 okay. Um, I'll write down your question and try to find out the formula in the notes. So you can tell me the formula. The sorry question. Can you repeat the question?
Same question, ma'am.
Yes, yes. Can you repeat? I forgot.
In the context of a
3D systems SLA.
process,
Hmm.
the gap between the doctor blade
Hmm.
and the pre-built layer is 10 microns or micrometer.
Hmm.
What will be the obtained thickness of the layer? Can I say the options also, ma'am?
Is it 5 micron
Ah, yeah,
or
ma'am.
there was a formula. What I can remember is the thickness between doctor blade and the pre-built layer should be double the thickness of the layer that you are expecting. So it is there. It is there. I cannot find it in my notes, but it should be 5 micron because I remember the thing like you understand, you have to make the thickness between the doctor blade and the pre-built layer. It should be two times the layer thickness that you are expecting,
Okay, ma'am.
because the doctor blade, when you are moving the doctor blade, where is my pen now? I can find it. When you are moving the build plate, this is your pre-built layer, and this is your doctor blade. So you will have something like this. So because of the viscosity. So when this is your pre-blade layer and this is the doctor blade is wiping. So this is why it is recommended that you always maintain the gap between this thing as two times, so that because of the viscosity, when you'll stop at this position from A to B, this thing will be like this, and after the Z wet, you'll have this, and the doctor blade has wiped out at this distance. Okay.
Okay, ma'am.
Any other doubt you are having?
Another one, ma'am.
Yes.
In AM process,
Hmm.
the maximum possible layer overhang can be 1.5 mm.
Hmm.
The build direction is positive Z.
Hmm.
The critical value of the Z component of the facet normal of triangles
Hmm.
of an STL file
Hmm. Hmm.
beyond that the support is, is be required is minus 0.75.
Okay, again, it is truly a formula. I remember it was discussed in the lecture. Maybe you can just go through the lecture videos again, or you can just note down the formula from the lecture. I don't remember the formula, but it was there that until how much you have to have the support, and after which distance you don't have the support. It you can estimate it from your STL file.
Okay, ma'am.
Yeah. I'll try to find out the formula from my notes. If I find out, I'll discuss it next class. If you find it out, that will be very good. Then you tell me in the next class. Okay?
Okay, ma'am.
Okay. Any other doubt?
No, ma'am.
Good. Then we can stop our class here.
Thank you, ma'am.
Thank you. Good night. Bye.